Everyone, so we'll solve this problem of step bar in Hypermesh Optistruct. So this is a step bar having the length 300 mm, 400 mm, and the area of cross section is given here, and also the properties of the materials are given. So we'll model it first as a 1D bar element. We'll apply the load P equal to 200 kilonewton at the center point, and we'll check the results and we'll see whether these results will match with this problem which is solved in Chandrupatla. Okay, so let's begin. So this is Hypermesh. Before that, I need to create the two materials because there is a aluminum and steel. These two materials are there. So I will create a material. First one is the steel, and since this is a isotropic material, I will take the card image as a matte one, and so these are the default properties. I will check whether these are the same. So steel 200 and it is a 210, so it is a 2 e raised to 5, and density will remain same. Okay, so we have created the one material and it will appear here, that is steel. I will create another material, that is aluminum, and created it, and the properties will be here. It is a 70 into 10 is to 9 Newton per meter square. So here it will be a 0.7 e raised to 5, and this is density will be is to minus 9. Okay. So if you just click it here, steel, so these properties will appear here. You can see all dimensions is in megapascal, right? So for aluminum, the properties will be here 70 into 10 raised to 3 MPa, megapascal. All dimensions are in Newton per mm square. So we have created these materials. Now we have to create these sections, okay? Because this area we have to give, and we can consider this section is a rectangular section. So we have to create the hyperbeam section here. So 2400 and 600. So accordingly we have to give the, now we have to create the cross. So this we have to areas of the cross sections for this beam, we have a bar, we have to define it, and for that purpose we need to create the sections, and that will create in a hyperbeam. So hyperbeam will take the here uh, standard section, and here we'll select the this standard section library as a hyperbeam, and here we'll select the solid rectangle as a section type. Then we'll say create, so will appear, we'll get another window, and this area 2400, so this can be a cross section we can define in such way that area will be a 2400. So we can define this as a 60/40, I think, 60 and 40, 40, 60/40. Okay, so this will be a 2400. Then we'll go to the model again, and another will create where the area will be 600. So 600 means 30/20, we can create 30, and this will be a 20. Okay, so immediately you can see areas here, area maybe here, area, yeah, this is area here, you can see 600, and for this area is a 2400. So both sections we have created 60/40, and this is a 30/20. So we'll go to the model again, and now we have created. So this all these sections will appear here. So the first is I will say this is a aluminum, so I can rename this. Then I will say second as a steel, so I will rename this. Okay, so now we'll create the property, and so aluminum bar. So this material is aluminum, and this section will be a first section. So we say create property. Second property will create, that is a steel bar, and material will be a steel, and this will be a section 2, and create it. Okay, so we have created the this, and now once you create this, we'll create the node points here, here, and here. So distance is first node point we'll create as a, go to the geometry page, nodes. So we created the nodes, it will appear here. The second node will be at distance of 300 mm. All dimensions are in mm. So create node. So second node will be here, and third node will be 700. Right. One more node will create, and that will be a 700. So you can see all these three nodes are created. So we'll create a bar element directly. So this is a bar element, and here orientation will keep y-axis section perpendicular to the y-axis. Property will be a first aluminum bar, because in our this is aluminum, so we'll create aluminum bar, and from this to this it is aluminum. Then we'll select the steel bar, and from this to this it is a steel bar. Okay, so this way it is created. Component, we can rename this as a step bar. No, because there are two components, so I will create, we did one mistake. So aluminum bar, that is one component. Okay, and one more component we have to create. We'll create one more component, is one more component, steel bar. So two components are there. So we have to organize the elements. So this is organize components. So first component will be a this will this sorry we'll select the elements instead of components. So organize, and organize mesh elements to component. So this element we have to organize as aluminum move. Okay, and this element we have to organize as a steel. So these two separate components are there. So for this component, so if you go to the, so for this component, when you have this component, the property is for aluminum, that you have to assign, and for this component the property is steel, that you have to assign. Okay, because these are the two different components. So now we have to give the boundary conditions. So we'll create the load collector here, and suppose force we'll give the red color. So we create the force. Second boundary condition is the single point constraint, that will select this color, will create this. So when boundary condition is force, we'll go to the analysis, and we'll see the force, we'll apply the force here, and that force is how much, no sorry, force no return. So we have to apply the force, and the force we have to apply here. And what is that force? Is a 200 kilonewton. So it is a 200, 123 kilonewton. So this is how force is applied, and when the boundary condition is this, then it is fixed on both this as well as this. So we'll select the constraint, this and this node, and we will create the constraint. So it is fixed on both sides. Okay, so we have to define the types of analysis. So we'll create the load step, and here we select the types of analysis as a linear static, and single point constraints are the SPC, and load is a force. Okay, so this is how. Then we can save this, save the session somewhere, and we can see these are step aluminum and steel bar. Okay, bar, that is aluminum and steel. So bar, you can save this. Okay, then we can go to the Optistruct and simulate this. So analysis is completed. We can go to the results. So, so this will appear here, and we'll see the contour. So here displacement apply. So we got the maximum displacement 2.3. Okay, so we'll check this whether it is as per the this value. We got the displacement as a 0.23. Yeah, so this is 0.23 displacement, and these displacements are always almost 0, 10 to minus 6, so these are almost 0. So we can check the nodal displacement also like this. So node, we can go to this point. So nodal displacement is 2.3 here, and this nodal displacement you can click, it is 0. You can click this nodal displacement, this is 0. Okay, so you can select the stresses, element stresses, and averaging method simple, and apply. So maximum stress is 54 MPa. Let's check whether it is there as per this. So here 54 MPa we got, and minimum stress is minus this. So if I go to the element stress, so element, so if I select this, so this is element connectivity, but stress is element this. Okay, that's why it is not showing stress. To component maximum 5.4, 54, and here it is showing 160. So this element stress. So as per this, we go get the same results.